It takes an enormous amount of propellant to take off from the surface of Earth and to fly out into space. But when you're coming home, there's a free lunch that you get to take advantage of, that the atmosphere can slow your spacecraft down to the point that it can land with a parachute or even land propulsively. And this is a great opportunity, but it is also very dangerous. You have to essentially shed all that velocity. If you were in orbit, you were going 28,000 kilometers per hour, and you need to get to zero. You need to convert all of that velocity into heat to slow yourself down so that you can land. There are several solutions to deal with this. There is, of course, the ablative heat shields, what we saw in the Apollo era. There are the thermal tiles, like what we saw on the space shuttle and on Starship. And my guest today is working on a third way of trying to keep a spacecraft cool as it's re-entering the Earth's atmosphere, and that is to have it sweat. So my guest is Dr. Hassan Saad Ifti. He's an assistant professor of aerospace engineering at Texas A&M University, and he's the director for the Laboratory for Hypersonic Vehicle Protection. And Dr. Ifti is working on the technology of transpiration cooling. This is where your spacecraft will bleed gas that will act as a thermal layer to protect it from the heat of re-entry. And it is very challenging. It's an idea that people have been thinking about for a long time, but we're now at a point with the technology, with the materials, with 3D printing, that this might be a reality. So if you're interested in this topic, enjoy this conversation with Dr. Hassan Ifti. Hassan, give my audience a sense of just how dramatic a re-entry into the Earth's atmosphere is on a spacecraft.
Hey, well, thanks, Fraser. So that is a good way to start, I think. So what is the challenge of a spacecraft re-entering? And why do we hear about the re-entry problem, the re-entry heating, for example? So let's start with rubbing our hands. So if we rub our hands against each other, we generate heat and we feel the warmth. So think about a vehicle traveling at 17,000 miles per hour. That's an enormous velocity, right? Enormous speed coming in. So when you're coming back from orbit, for example, that's the speed you're going to plunge into the ocean with. So imagine the friction you will have with the surrounding air in the atmosphere and your vehicle's skin. So you're rubbing against that atmospheric gas, in this case air, at that speed.
Right.
So that would
rubbing your hands together at 28,000 kilometers per hour.
You're going to burn off your hands, right?
Very quick.
So think about it for a second. So this is why what happens is that friction, we call it aerodynamic heating, it leads to the gas becoming hotter and hotter. And your gas temperature around the vehicle would become more than 10,000 degrees Celsius. And think about it, we don't really have a material that can withstand that sort of temperatures, right? But we still have spacecraft coming into the atmosphere and returning back home, and we say coming home. So how do we do that? So all of that heat around that vehicle would eventually go into the vehicle and make the vehicle itself hotter. So the key here is to reduce that transfer of heat, that outer, say the heat in the outer gas, to your vehicle. So this is why we have ablators. So if you look at the Apollo capsule, for example, they had a huge ablator as the heat shield. So heat shield, that's a general term. So to protect the vehicle from this enormous heating that goes on, we use heat shields. So ablators are one. So ablators would sort of sacrifice themselves and melt away as the vehicle comes in. And the second type is the space shuttle type. So you have all these tiles that get hot and then radiate out the heat back to space. So that's kind of how we deal with the heat problem at the moment. But it's actually for any given mission, the re-entry problem, or if we're going to, say, from Earth to Mars, the entry to Martian atmosphere, that's actually one of the hardest phases of the whole mission. So this is why it's so important. You can have a very successful mission, but if you can't bring back your craft home, then you don't really have a complete mission. And that's one of the hardest things, if not the hardest phase of any mission to space.
But I always consider the ability to do an atmospheric reentry as a free lunch. That if you were trying to land, if the Earth had no atmosphere and you were trying to land safely on the Earth's atmosphere, you would have to perform your launch in reverse using a certain amount of propellant to get yourself back down to the surface of the planet. It's what you have to do when you go to the moon. But when you go into a planet that has an atmosphere, then you do get to take advantage of that atmosphere as a way to slow down your velocity. And so, it's more like, how do we take advantage of this free
Fraser,
return?
that's a great point. Yes, and that's what we would say is aero braking, right? So
Yeah.
if you come back at these speeds, imagine coming back at 17,000 miles per hour, and you don't have an atmosphere. How do you even brake? So it's actually a benefit that we have the atmosphere to brake. Now, you're absolutely right. We use the atmosphere to brake and essentially slow down the vehicle. So what's happening here is we have an enormous amount of kinetic energy. Now, with the atmosphere, we can, by design, slow down the vehicle so that kinetic energy gets translated to mostly heat. And so it would dissipate as heat as the vehicle slows down. It's like when you're driving say on the freeway, right? When you're driving a car at, say, high speeds and you want to brake right away. If you have a sudden brake, your brakes would become hot, right? Where would the energy go? We need to transfer it somewhere. So this is why if you look at, say, re-entry vehicles such as capsules, these are really blunt bodies because you want to really push the air and slow down. Now, although that is something that we use and that's a benefit to us for the mission, we still need to deal with the fact that we have this energy, that enormous amount of kinetic energy, and we need to transfer that to a different form of energy. And, the natural way of doing it is always by heating. Now, how do we manage heat? So at the end of the day, this is thermal management. How do we manage the heat? So when we design space vehicles, spacecraft, re-entry vehicles, we want to design it as such that all of that heat that is in front of the vehicle or around the vehicle, say above 10,000 degrees Celsius of gas, that it doesn't come into the vehicle. So that's the science of heat shields.
I guess with the profile of the atmosphere, you've essentially got 100 kilometers to work with. That at the beginning you start with this orbital velocity, and at the end you want to be zero relative to the ground, and you've got this entire volume of air to work with. But it seems like as vehicles are re-entering, they're heating up very quickly, and then they're able to use parachutes, or with the space shuttle, it was able to use aerodynamic lift to be able to move. So do you have any control over how quickly you bleed off that velocity through the column of the atmosphere?
Yeah, that's an excellent question. And this is actually what we consider when we design, for example, a trajectory. So let me show you an example. I'll use my water bottle for this. So as the rocket comes in that trajectory, you're starting with very thin air. So at about, say, 80 to 100 kilometers of distance, there isn't really much of air molecules up there. So as you come in, you're coming in with within a very low density gas. So that's the air having low density. As you come in, you're coming into a thicker atmosphere. Okay, so now what happens is when you actually plunge into the ocean, the air is not as dense as what we have down here. So we would have the highest velocity at that level, and that's where actually we bleed off that energy and velocity. Now, this is an important question because up there, unlike when we fly today, the flow, because it's so low in density, the flow is laminar, it's the smooth flow. Now, if we look at, say, if we have the same conditions and have a laminar flow, which is a smooth flow around the vehicle, versus a turbulent flow, which is a chaotic flow. It's like when you mix your coffee and milk together, rigorous mixing. So the heat fluxes that go into the vehicle when you have a turbulent flow is 10 times higher than what you would have for a laminar flow. And this is why it's so important, because you want to bleed off most of your velocity and energy in the laminar regime where say the atmosphere is thin enough. So you often have, for most of the trajectory, you could design it as such that the peak heating, the highest amount of heating that goes into your vehicle, happens in the upper atmosphere where the flow is still laminar. So the heat flux that goes into your vehicle is not as high. And then once you actually bleed off most of your speed and energy, then you enter sort of the thicker part of the atmosphere and your flow becomes turbulent, but you can still manage it because now you're not as fast. So the faster you go, the more heating you have, right? So, but now that you have less velocity, even though you're becoming turbulent, the flow is becoming turbulent, the heat fluxes are not that high. Does that make sense?
Yeah. So are there ways to remain in that laminar flow region for longer? I mean, I know that, say, the capsules have an aerodynamic shape. The space shuttle had, I mean, it was more like flying a brick, they said. But, do you want to try and kind of maintain your altitude for as long as you can before you finally do that drop off into the more turbulent air?
Absolutely, Fraser. Yes, that's what you generally would want to do if you want to make the vehicle survive. So that's part of your trajectory design, and it will. And of course, if you want to have a, for example, say reuse the vehicle, you would need a technology like that. So where you reduce the amount of heating going in. So this is why you would absolutely want to bleed off the energy in the laminar regime before you hit the thicker part of the atmosphere. Absolutely.
Right. All right. Well, so the reason I reached out to you was you've got a new press release, a new research that you and your team are working on to consider another method of removing heat from a vehicle, something that we're all very familiar with.
Yes. Well, absolutely. I'm very excited about this project. So this is really, I think the title sort of says it's a sweaty spacecraft. So it's super interesting as an idea. And this idea, by the way, has been out there for a long time. As we like to say, we're standing on the shoulders of giants.
Yeah, I always say that every good idea is in a NASA technical paper from the 1960s.
Exactly. And if you look up transpiration cooling, you're going to find papers from the 1960s and 70s on transpiration cooling, right? And it's a nice way of putting, saying that the rocket is sweating or the spacecraft is sweating because that's what it's doing. But ultimately, I think, I will go into the details, of course, but I think I'll answer the question, why now, right? We had transpiration cooling. Why do we have it again? And I think we have a major movement to make spacecraft and space vehicles reusable. We have better experimental capabilities, better simulation capabilities. And again, with the excitement in space, we get a lot of talent coming into the sector again, right? I just wanted to put it out there that it's an extremely exciting time for everyone in space. So this project is really about reusable rockets. Do you want to start with a specific question there? Or?
Well, I mean, I guess like, what's the idea? So like, the idea of transpiration, like you're going to be, your spacecraft is going to sweat. Why does a sweating spacecraft make more sense or, is interesting, worth exploring compared to an ablative shield or something like the space shuttle's heat tiles?
Why does it matter? Why do we want to have a gaseous layer? So I'll go back to, say, ablatives and, say, the ceramic tiles, for example. Both of them actually get some damage as they come into the atmosphere. So ablatives, they would pretty much be not reusable. Ablatives are not reusable, so they're totally damaged when they're back. When it comes to the tiles, think about the thousands of tiles on what we had on the space shuttle. But also on the Starship, the new rocket that SpaceX has. So after a mission, you would have to go through an inspection process. and make sure that each tile is intact and they're not damaged. And if one is, then you'd have to swap it over. So you have refurbishment time, cost, and labor. So what happens with that technology is that before you can go again and reuse the vehicle, there is a time, say, anywhere between 3 months to 6 months, roughly speaking, before it's ready. Now, the goal we have in the community, of course, in the reusable rocket community, is to use a rocket just like an aircraft. You go to your destination, 90-minute turnaround, and they're ready to go again. Just like we use our cars today, right? We can go to the supermarket and then come back, and we're using it several times, thousands of times, right? So that's essentially the idea behind it. That's the goal behind it. Now, what's the idea with transpiration cooling or a sweating spacecraft? So gases are really good to insulate heat. So they have low thermal conductivity compared to, say, metals or solids. Now, think about I love this example of a puffer jacket. So, and that's in the article as well. I use that as an example. So in the winter, if you wear a puffer jacket, what's happening is that you have air around you. It's a jacket of essentially air. You have air pockets. So that air is trapping the heat from your body so that it doesn't escape. This is how you stay warm. So gases like air, they're good insulators, thermal insulators. They keep the heat away. So think about a case where if we could have a jacket on top of a rocket, like an air layer, a layer of air, right? What it would do is it will keep the heat from the outer gas away from my vehicle surface or my vehicle as a whole. So I'm using it as the opposite direction, of course. Instead of trying to trap heat within the vehicle, I'm trying to keep it away. So the question now is, okay, how do I actually have a layer of gas around my vehicle? How do I keep that? Because it's just going to go away. It's going to mix away. So, and this is an important, I think, aspect of transpiration cooling is that the mixing of the gases, but we'll get there in a bit. So because we can't keep the gas, we want to continuously inject that gas from the vehicle's skin. So this is where transpiration cooling comes in. It's mimicking the way we sweat. So just like we have pores in our skin, we'll make the rockets or the spacecraft's skin out of a porous material. So you will have tiny, tiny holes. And now you can, from within the vehicle, from pressurized reservoirs, you can inject a gas. So it comes out and then it will form that layer. And you'd have to continuously inject and make the spacecraft sweat for that duration of reentry. And again, because the layer that you create might mix with the outer gas, and it will. So that's the science we're after. We want to know how it really occurs so that we know how much gas we have to inject for a given duration. Does that make sense? Because it's going to mix away, right?
Yeah. So I think about, you mentioned sort of two concepts here. One is that you're getting this insulating layer around your spacecraft that is preventing the heat from reaching the actual spacecraft itself. But when I think about the process of sweating or just evaporation in general, it is extracting heat from the environment and takes a large amount of heat to turn a liquid into a gas. And then I'm assuming this stuff is falling behind the spacecraft. And so you're taking all this heat and you're shedding it in addition, as if you were shedding the chunks of your ablative shield.
Yeah, exactly.
And so,
yes.
Yeah. And so is it both of those factors happening at the same time that are giving you this advantage?
I'll just add here, ablators actually work in a similar way. So ablators are solids, of course. So once they're in action, they actually go through a process of pyrolysis. So from solid, you have gas ejecting, right? So that sort of pushes the hot gas away. In transpiration cooling, the difference is that it's it's active. So I'm not damaging my shield, say on the exterior, but I am actually injecting either a liquid or a gas, and I can replenish it from within. And once my mission is done, I can go and refuel my coolant tanks and go again. Now, you touched on a very important part there, is you mentioned liquid. So transpiration cooling can happen in at least two ways. So the first one is just gaseous. So you inject gas, not liquid. So say you take a tank of helium and you inject helium. And helium is really nice because because it's a lighter gas, it takes up more volume as it's injected outside. So it pushes the hot gas away. But you could do two-phase transpiration cooling, where you have the liquid injected through the pores, and then it will extract the heat within the porous material, and then use that heat for phase shift. So now from liquid to gas, it needs that energy, that latent heat. It will extract from the porous material itself. So by doing this, you'll cool down the wall, and then it will eject as a gas. So here you can actually use that latent heat to further cool the vehicle. And then, of course, what you have is all of that gas that is expelled out of those pores. Now they form this layer of gas on top of the vehicle, which is your insulator. But also, the other thing is, you can inject gas in the upstream, but all of the gas they're injecting, it's traveling downstream. Although it's mixing away, you have some of it downstream, so it's keeping your vehicle cool even on the backside. So there is that residual effect that's helpful. Now,
right. And so it doesn't matter. I mean, you're going to need to have emitters across the spacecraft, but it still is going to provide enough of a layer that I think about what happened with the Columbia disaster, where a chunk of the foam knocked a piece of the tile off. And when they came in, you had to be perfect. And because there was one little gap in the heat tile, that's how the hot gases found their way in. And that led to, after every single shuttle launch, they had to deploy the boom, examine the heat shield very, very carefully, make sure there weren't any issues. And if they did, they had to go out and patch it and so on. But with this, are you saying that you get this sort of general protection that allows you to then not have to be so extremely concerned about every single nook and cranny of the entire spacecraft?
Exactly. Well, that would be the goal, the ultimate goal with it. And if you ask me today, I would say, and this is also I think, the general, say, idea in the community is that transpiration cooling would probably augment something that we already have. So say ablators and ceramic tiles. So wherever you have hotspots of heat, for example, if you have a vehicle coming in with ceramic tile, then you see there are certain spots, like when you have leading edges, for example, the leading edges of fins, the nose. Those are the locations generally where you have the highest heat loads. So those are the places where you get the damages. So if you have transpiration cooling there, then probably as a mixed, say, heat shield solution, you would be able to have a fully reusable vehicle. And I really emphasize on the fully part, the full reusability, not a degree. We really want to have full reusability. Now, one thing I'd note here is, just like, say, the case of Colombia, for example, you don't want to have something that's disruptive in the flow field. So when you inject that gas, the coolant gas, you want to inject it in a way that's nice, that's uniform, that's not creating fluidic roughness, right? If you have a jet coming out here and a jet coming out there, then you have rough fluid coming out of the vehicle, right? Which would then also promote the flow from, say, being laminar to becoming turbulent. And again, that's at least a 10x rise in heat flux. You don't want that. So this is where the science comes in, right? What is the science of transpiration cooling? What is the physics of it? And that's something we're trying to study here with our tunnels, of course, so experimentally.
Now, obviously, it's about the weight. as well, right? That there's going to be some kind of weight dedicated to this system compared to the weight of an ablative shield, compared to the weight of the tiles. So even if this thing is significantly heavier, there's value because it decreases that refurbishment time. But the ideal, of course, is that this is also lighter. Where do you think a system like this will come in from a weight standpoint?
That is actually the key question um, to addressing the added value of transpiration cooling. Now, in general, transpiration cooling might actually add more weight than your ablative systems or your ceramic tile. So, and why is that? Because first of all, you have to carry the gas, the coolant gas with you. Say you want to go from Earth to Mars, come back again. So you require coolant for entry to the Martian atmosphere, which is, by the way, predominantly carbon dioxide. So the physics of your transpiration cooling would be a little different. Now you want to come back. Now you have re-entry to Earth. And again, here, transpiration cooling, now you'd have air. So again, a different set of physics. But you're carrying all that gas with you. And probably you would add a safety factor to it. So first of all, you have the mass of the coolant. And you can only determine this mass of coolant if you know the physics of transpiration cooling, right? So you have to know your trajectory and how it works out with your physics. So that's one component. But then you have a whole system in your vehicle to feed that transpiration cooling system and then inject gas into the pores. So you'd have your pipe work, you would have a complex system within. So when we test in the wind tunnels here, for example, our experimental model would look fairly, say simple from the outside, but from within, it's actually fairly complex. And that would add more weight to the system than your conventional ablators and ceramic tiles. So this is, I think, one of the questions to ask for a technology like this. But the answer is not so immediate because it depends on your trajectory, your mission, right? For some missions, we might see that actually having transpiration cooling might reduce the weight of the heat shield. Let's say the thermal protection system as the heat shield as a general term might actually reduce your weight. But for other missions, it will actually add weight. So if you have to carry, say, say, if half of the rocket is coolant, where do you put your propellant, right? So now you're asking all these questions about, okay, how do I optimize my mission for it? So I think at the end of the day, the clear winner, say, would be a system that's a mix of different heat shield types, where transpiration cooling would, I think the clear added value is the reusability. Right? This is something you can really argue about. Like this really adds the reusability component to the say solution. But whether it's going to reduce weight, that's not an immediate say answer. And likely it would add more weight. So you would have a vehicle that's heavier, but for that, it's reusable.
But there are, I guess, sources of gas that are on a spacecraft. When I think about, say, in order to keep tanks, the propellant, the remaining propellant in a tank, they're often forcing like even helium gas back into the tank to try and keep it under pressure and keep the propellant where they need it to be. And so I can imagine some situation where, like right now, that's just kept in or maybe vented later on. But maybe there are ways that you can use that as a resource later on in the mission to help with the heat shielding.
Yeah, that is, I think, that's exactly what we should do. Yes. So part of it is really, part of the work we do here is looking at those aspects. So the physics would change depending on the gas you use, right? Or the liquid you use in this case. So we really want to understand as a general solution how the gases dictate, say, the mechanisms behind transpiration cooling. So this is why we want to test out an array of gases and liquids so that we can then pinpoint, okay, if I have a few gases or liquids already in my vehicle. Can I use that? Right? Like, for example, you could use methane, right?
Yep. Astronaut
Um,
urine.
yeah, yes, maybe, yes, yeah,
Yeah.
instead of maybe putting it out as a waste, maybe we can use it as a coolant, right?
Yeah, there we go.
It's not, I mean, we laugh about it, but maybe it's not that
Yeah.
far off,
Yeah. Yeah. You're going to bring back a few kilograms of it. Might as well use
Yes.
it. Yeah.
Yeah. But this is exactly where kind of our approach is going, is to understand the fundamental physics behind it, so that we can really pinpoint, okay, if we already have a certain amount of gas or liquid in the vehicle, and think about the fact that, if you have a cryogenic system inside, we can also maybe cool, a liquid so that it stays in liquid form, and then do a two-stage or two-phase transpiration cooling with that. So these are all the big questions that we're again starting to question and then answer. And hopefully we'll have a lot to do in this little field.
From a physics standpoint, is there a perfect gas? Is it helium?
Yeah, that is. I think that's a question that has been asked in several sources, but also types of R&D and engineering. And I'll give you an example here. So something similar like transpiration cooling is being used every day. As we speak, it's being used. Where is it being used? Gas turbine blades. So gas turbine blades operate at a temperature that's higher than the melting point of the alloy that it's made of, but it survives. So the reason is they have film cooling. So film cooling is where instead of a porous surface, you have discrete holes. So you can if you hold the turbine blade, you can see the holes. So they inject, essentially what they do is the compressed gas that is taken in by the engines, part of it would go into these blades and be bled through these blades. So that's how you have a similar, say, approach of cooling. So we call it film cooling in the industry. Now, if you look at the film cooling world, they have extensively looked at this. And generally speaking, any gas that has a high specific heat capacity. So these are generally, you'd say, even hydrogen, for example, has a very high one. Helium has a high one. So helium has been known to be a good coolant because of it. So it essentially can absorb more heat. That's one way of thinking of it. Now, in my experiments in the past, what we have found is um, helium is not only good because of that thermal property, because that's one of its thermal properties, but it's also good because of its physical properties. So compared to, say, when you inject nitrogen, helium has 7 times more volumetric flow rate. So it creates, for the same mass injected, say you have think of maybe a transpiration cooling system that has 1 ton of coolant gas. Now, if I compare it to nitrogen versus a helium case, helium would, for the same amount injected per unit time, helium, because it's lighter, it generates a thicker film physically. Like, we don't even have to go to the thermal properties yet. It just pushes the outer gas away. So you have this intended effect more, say, easily than, say, nitrogen. Right? If you use a gas like argon, a heavier gas, it would be slimmer. Now, in some cases, you might actually want it because you don't want to really disturb the outer flow as much. So going back to your question, it's a case-by-case analysis depending on your mission. But generally speaking, gases, if we look at the gases, helium is a good coolant. But it comes with that penalty of volume, not necessarily weight, but volume. And I'll add to just to add to this, and this is super exciting, I think. In our research and in the community, we have found two gases, so one helium and the other one is carbon dioxide. If you inject them, you can delay the transition to turbulent flow. So just that mechanism might allow you to delay transition to turbulent flow so that you stay laminar and thereby keep your heat fluxes 10 times lower.
Right. Even while you're potentially entering a region of the atmosphere that would be
Yeah.
turbulent, you're
Mhm.
treating it like it's still laminar,
Mhm.
and that is allowing you to like stretch out that heat sort
Yes.
of amount that you're having to give off
You can
over a
stretch out
longer
that
period of
corridor
time.
in your
Yeah.
trajectory. Yes. Yeah.
Oh, that's really
Yeah.
interesting.
So the immediate answer is, there are a few gases maybe that are maybe better than others. Yeah.
But then other gases, but then you sort of think about the cost as well. Some are easier to get your hands on than others. Trying to fill a spacecraft with a bunch of xenon gas as a way to slow yourself down, that sounds expensive. But hydrogen is relatively easy to get your hands on compared to, say, helium. But of course, hydrogen has its downsides. But I think about...
Yes, exactly. Yeah.
But hydrogen, like, people are considering space-based refueling systems, and trying to keep cryogenic propellants in space for long periods of time has proved to be very difficult. And one of these reasons is because hydrogen especially is sneaky. Like, it just wants to get out of whatever bottle you put it in.
Yeah.
But in this case, that's kind of like a behavior that you're looking for. You're like, once you point it to the door and go, here's a trillion little holes, be gone. It's going to be happy to take all those little exits out of your spacecraft.
Exactly. Yes, that's actually like we actually use helium to do leak detection, right? Because helium has a similar effect of trying to escape from every.
But
little
is
corner.
hydrogen even more so?
Yes, hydrogen is even more. I think the difficulty with hydrogen, on paper, hydrogen is excellent for even cooling purposes. But I think the difficulty is again the safety aspect of it.
Yeah.
And
it
adds,
exploding.
it adds a lot of difficulties, when you want to do, even if you wanted to do an experiment, that has a whole different set of safety regulations attached for it for good reasons, of course. So I think, I think helium is a good substitute, but again, it's not a final answer, right? There is a lot of room to look into these, and I think if we have, for example, if we have a hydrogen, say, if you have a vehicle that uses hydrogen as propellant, now that's where you can think of using that also for some of the cooling aspects. And then if you have a complex system to keep the hydrogen, you're not just doing it for cooling, but you're doing it for propulsion as well. So this is where I think these opportunities come in. So this is why if I hope anyone who's watching your video here, there is a lot of room to improve and bring new ideas here, and look at what gases are actually good for what uses. So again, it's a very exciting time to do this, and these are open questions to some extent. Although again, if you go back to the literature, you'd find starting from those NASA technical notes, you'd find a lot of positive studies on it. But the question is, if I wanted to make a vehicle today, what do I need? Like, is our knowledge mature enough to do that? Like, I want to have a vehicle now with transpiration cooling for a given mission. Go. What do I do?
And I'd like to spend a little bit of time just talking about like how you would potentially construct an outer shell of a spacecraft. I actually got to tour SpaceX about 10 years ago, and they gave me a piece of titanium that was 3D printed, and it felt like a block of titanium, but you could hold it up to the light and you could see holes through 5 centimeters of titanium, little holes all the way through it. And so is the kind of the 3D printing technology at the state now where you could actually print this stuff off?
Yeah, I think that is a great way to connect, say, what we're doing here, right? That is, again, one of the questions is, why transpiration cooling now, where, we already talked about this decades ago. And one of the advantages we have today is, as you said, the 3D printing of even materials such as titanium is readily available, and it's becoming better. Say every year, we see, the resolution that they can do. So how small of a detail can you make, right? It's becoming better and better. I can recall, like, about 8 years ago, I looked into like metal 3D printing for a different project. Um, and it wasn't as great as it is now. So now we can be more creative about how do we create the skin of the vehicle, right? And we can design the skin of the vehicle tailored for transpiration cooling. So, for example, now why would you want to do that? So you would want to have the porous material, the porous segment, the skin of the vehicle to be, say, first of all, uniform. You want to have the flow, the injected gas, the coolant come out in a uniform fashion, not random. You want to have some control over it. And the second aspect is, if you look at, say, the reentry, say, rendering or any photo of reentry, you would see that a spacecraft generally has more heating at certain areas than others. Like if you look at the heat map, it has some sort of a distribution, right? So now, if we design the skin of the vehicle according to that distribution, so you inject more where you need more protection versus less where you need less protection. Now, that's not only nice engineering wise, I mean, it's beautiful engineering if we can do that, but it's also saving the coolant mass. So if I don't need coolant in certain area to a higher level, why inject more, right? And this is where, if we want to have a working transpiration cooling system, we really need to nail the way, say, we design the system, right? Which is really predicting how much coolant we need in those locations and how much we need to carry with
And
us.
and are you? I mean, are you predicting, or are you able to maybe even react? I mean, I think about sort of in the world of observatories in astronomy, they have these this adaptive optics where you fire up a guide star into the sky and then you measure the atmospheric distortion of the star, and then you use that to change the shape of the mirror in real time to adapt to what it is that you're actually seeing. And I can imagine, the atmosphere isn't going to behave the way you're always expecting. In fact, and so you could be sensing different temperatures and go, nope, a little gas over here, a little more gas over there.
Yeah, no, absolutely. And this is an excellent statement. I think this is how, if I look at the future and I sort of, if I have this idea of a transpiration cooled system, it would have a nervous system. So not only can the atmosphere change, you may have to change your trajectory. So when you're coming into the atmosphere, right, in every point of that trajectory, your velocity, pressure, temperature, and therefore density, they're changing, right, at every point. So from trajectory A, if I have to move to trajectory B, now I have a whole different scenario. So the flow conditions are very different. So now, if my vehicle does not account for it, I wouldn't have a successful system. So as you said, the vehicle should have a nervous system that takes that into account. What is the heat coming in? What is the flow conditions around me? And that will go back to, say, the computer to tell it to intelligently then inject the gas where it's changing. Say, if it needs more, it would do more. But for that, what we need is a good understanding of the porous material that we have, and that has to be designed in a way that allows this. So just to give you an example, say you have a vehicle nose, right, and you make it porous. And because of the trajectory change, now you have to double the amount of gas that should be injected. And you have that in your gas tank, that's fine. But if you double it, now you have to do it by pressure. So you increase the pressure, for example. So this means that the porous materials should allow the flow going in. So this is porous media flow, essentially, coming into this. And by the way, I'll just make a comment here. porous media flow is very slow, and reentry flows are very fast. So we're combining like a teeny tiny flow speed versus a high speed scenario. So in this case, when you need double the amount, you would actually, if your porous material is not designed the correct way, you might actually apply a lot more pressure on it than it can withstand, right? So it's not going to be an immediate solution of let's just crank up the pressure, right? So, and then what you might see is at high pressures, the flow may come out in a way that you don't like. So this is why we want to really tailor the porous materials for the purpose of transpiration cooling. And this is where, again, coming back to your statement there with 3D printing, we live in a time where we can't think of these ideas. So we were sort of reimagining how we would do this because we have, to some extent, full control over the porous media.
Hassan, what are you obsessed with right now?
Well, right now, and I think to a larger extent for most time, I think I'm really obsessed with, a future where we can travel as just normal human beings, just go to space, come back again, go anywhere within the world, like within 2 hours, right? I think I think that's a beautiful future to have. And I would say, day in, day out, I'm pretty obsessed with that goal, that vision. And the vision I have is to really have, contribute to the world of next generation thermal protection systems. So next generation heat shields. That has been my, so say, life's work for about 9 years now. And I think if you ask my friends, they would say, I'm obsessed about it. It's, and I'm very lucky that I get to work with extremely talented people, and particularly very young people. So who are coming in as new students, for example, at my lab, for example, and bringing in new ideas, working with me to really have a future that we want to have. And I think also, your audience would agree that that's probably a very exciting future.
Yeah, I mean, I think I always say that our heads are really filled with science fiction on what the future of space exploration might look like, Star Trek, Star Wars. And then at the same time, many of the things that were imagined in this future have already come to light. Our phones are far more capable than any communication system that you see in science fiction. We're now having conversations with computers, which is super weird.
Mhm.
But it's that space flight part that we were promised, and there's so many details about every aspect of this. And it's great because I'm talking to a person who has dedicated his life to how do we keep these things cool as they pass through atmospheres, because that's like, if that part doesn't work, then everybody dies. So
Yeah.
I think it's a very important chunk of the work of the larger tapestry of all of the bits and pieces that have to come together to make this work.
Yeah, it's
So
essentially like, coming home, essentially, right? So how do we come home safely, right? So how
yeah,
do we
yeah.
protect that? And I think, that's, yeah, I mean, it's also, again, the times really are different now, very exciting times. So I really love to reiterate that. So, I really, whether I can do it, I don't know, but I think what I see, especially young people out here, I think, today or tomorrow, I truly believe, and this is not the scientist hat on me now, this is, just as a person, I truly believe in a future where that would happen. Like, I really do, that's, day in, day out, I do believe that.
Yeah, and as do I, and I think that's what got us all sort of into this, and
Yeah,
that's what sort of you're always sort of seeing that as your North Star. Like, that's our future, that we will eventually have this more capable, hopefully solar system spanning civilization, that we're not trapped on this planet if we don't want to be, and hopefully we'll be able to go and explore everything that this solar system has
absolutely.
to
And if
offer.
I may, take a minute to add another comment, if you think of like not even 100 years ago, we had, say, the luxury of the way we fly today, right? Like when we fly, hop on an aircraft, and we just take it for granted. But if we were to use an aircraft once, say a Boeing 777, say roughly it can carry, say, 300 people. List price is about 300, say, million US, so roughly speaking. So your ticket price would be $1 million US. And that's what's happening in space travel today. So, the day we have reusable rockets, the day we have, reusable hypersonic vehicles, think about the future, think about, not just ordering your favorite sushi from Tokyo, but if you have a donor somewhere, say in the US, and you want to donate, say, an organ in Singapore, it can go there within 2 hours, right? Like once we shrink the world, we shrink it forever. So, that's yeah. I just love to think about it. I think there's a beautiful future.
Yeah, awesome. Well, Hassan, thank you so much for taking the time to chat. I really appreciate it, and good luck with your research.
Thank you, Fraser. Thanks for having me, and keep up the good work.
I hope you enjoyed this conversation with Dr. Ifti. Now, we had an extended version of this conversation where we talked about hypersonic vehicles. So not just trying to protect your vehicle coming back from orbit, but how do hypersonic vehicles that may carry you from point to point here on Earth have to deal with the heat and the temperature as you fly. And it was interesting just to find out, when we might be able to fly point to point here on Earth, going from, say, Los Angeles to London in 2 hours, which would be amazing. So that longer version, we call that Interview Plus. It's over on Patreon. It's completely free. You don't have to sign up or subscribe. You can just click the link in the show notes and go watch that longer version of the video there. Now, I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylock, Cy Nielsen, David Gilton, David Matz, Dustin Cable, Evan Pro, Greg Feely, Hans Schultz, Hudson Ward, Jay Graves, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Marcel Smith, Michael Purcell, Modzo, Paul Roebuck, Ren Kaidu, Robeck, Sean Sargent, Stephen Fowler Munley, Thomas L. Skadron, Vlad Shiplin, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. The heat shield of Starship and the heat shield of the Orion capsule keep me up at night, because these are the ways that you have to keep your precious crew safe as they are returning from space. And as we saw with the Columbia disaster, if there's any challenge, any problem with the heat shield, it can be catastrophic. And so, we know that there's been some issues with the Orion heat shield. NASA is addressing them. Of course, Orion might get canceled based on the new budget, so who knows? But with Starship, progress is continuing. We're seeing more and more tests of that spaceship. But the part that I keep watching is what happens when it re-enters the Earth's atmosphere. Can they figure out a way to get that spacecraft down to the surface without it taking too much damage to its heat shield, moving toward that era of full reusability? And so I really like this idea, and something that Hassan talked about early on in the conversation, that it will probably end up being some kind of multi-part protective system where you've got some kind of ablative potential, you've got the heat tiles like what Starship has, and maybe you also are able to include this transpiration cooling system to try to keep your spacecraft safe and be able to minimize the amount of refurbishment that has to happen each time you fly. So we've got a bunch of interviews that are related to this topic, which we'll put some links in the show notes. I'm sure there'll be some around here right now. But I hope you enjoyed the conversation, and we'll see you next time.